Jtag was developed to help solve the problem of checking whether printed circuit boards were built correctly or not. So a manufacturer might churn out thousands of PCBs a day, put the components on, but due to faults in solder and other such things, some boards might be faulty. For example, maybe this pin is supposed to be connected to this pin, but due to a faulty solder joint, that connection's not there. How can you find that quickly? In the past, you could try to use a device with probes, so you could put a probe here and put a probe here and check whether or not there was a connection between the two pins. But this is costly and difficult, and it doesn't work when you have chips these days where the pins might actually be soldered directly to the board underneath the chip in a ball grid array format. So it's not even possible to get a probe inside there to probe certain pins. So this was the motivation for Jtag, but then Jtag found other applications as well and is now commonly used to upload code to boards. So to upload FPGA configuration files to our DE1 SoC board, we use a Jtag connection. And if you have a microcontroller board and you want to program your microcontroller, then often there'll be a Jtag connection that allows you to upload your code into some flash memory that the microcontroller can then run when it's booted up. Jtag is a special interface added to a chip. So chip manufacturers have to build in Jtag capability into their chips. One of the Intel processors, the 8486, was the first chip to have Jtag built into it, and since then a lot of other chips have adopted this. So FPGAs normally have a Jtag interface, microcontrollers normally have them, etc. And all that means is that each chip, this might be a microcontroller, this might be an FPGA, this might be something else. On your printed circuit board, you simply make these connections from a, in this case, a 4-pin Jtag header. You're just going to connect TMS to all the Jtag enabled chips, collect TCK to all Jtag enabled chips, and the TDI gets daisy chained through all your Jtag enabled chips coming to TDO. Here, TDI stands for test data in. This provides a way of sending data to each of the devices. And TDO, test data out, provides a way for the devices to send messages back to you. Remember, we're going to have a computer out here connected through a Jtag device that then connects onto this connector here. So the software on the computer can send and receive data, and this allows the software to communicate with all the Jtag enabled chips. This is not when your design is running, this is before in the test stage, and we'll discuss that presently. The TCK is the test clock. So we basically have a serial connection here, so we need a clock to regulate the transmission and reception of data here. And TMS is test mode select. This can be used to tell the devices exactly what we're supposed to be doing with the data, etc. Here is an example of a Jtag device. It simply sits between your computer and the board that you want to test or configure. Putting Jtag into a chip allows a Jtag device to take control of the pins of the chip. So if this were a microcontroller, then the blue bit represents the actual microcontroller, and rather than have the microcontroller pins go directly to the outside world, there's this extra little layer in here. And so when the chip's being used normally, Jtag is disabled and we just have a straight connection so that the microcontroller is connected to the outside world via the pins in the usual way. But if you connect up a Jtag device and you send the appropriate control messages, then the little Jtag controller here can disconnect the pins from the actual microcontroller itself. So the chip you buy is this white thing with the pins coming out, but you can think of it that inside the chip you buy is your actual microcontroller and this extra layer in here that allows the Jtag device to hijack or to take over the pins under certain circumstances. Originally, Jtag was developed to do a boundary scan. So the way this works, imagine we have two Jtag enabled chips and they're on our PCB. If we want to test the PCB to make sure, for example, that this pin is connected to this pin, then we just get our Jtag device to connect to both this chip, and it can ask this chip to send out a logic 1 on this pin, and we can read what value we get on this pin here. And then a bit later, we get it to send out a logic 0 here and read what's on this pin here. And provided when we send a 1, we receive a 1, and when we send a 0, we receive a 0, then we're relatively confident that we do have a connection between here. Similarly, we can check there are no solder bridges. We can send out various combinations of messages on these different pins here, and we can listen on this pin here, and we want to make sure that it doesn't matter what we're sending out on all these other pins, it should not influence what we receive here. So by being able to hijack the pins of the different Jtag enabled chips, we can send out test messages and listen to what we get on other pins. And in this way, we have a very cost-effective way of working out whether our board appears to work or not. It's the equivalent of applying probes to different pins on chips, but as you can appreciate, because we don't have to physically attach a probe anywhere in the circuit, it's a lot cheaper and a lot faster to do things this way. Moreover, if some of the chips these days use ball grid arrays, meaning that the pins don't come out the sides of the chip, but they're just little dots on the bottom of the chip, and you put the chip directly on the PCB and somehow solder it there, and you literally do not have access to the pins of the chip once you do that, so you can't probe them in a conventional way. Jtag becomes the only way of being able to probe what's happening at different pins on a chip. It did not take long though for people to realise that Jtag functionality could be used for other things. For example, if we have a microcontroller here on a board and we want to reprogram it, that basically means we need to put different code into flash memory, then rather than either build a separate programming device into the board or have the flash memory somehow being able to be taken out of the board by some socket and put into a programmer, instead of doing it the old-fashioned way, by using a Jtag device, because we can hijack the pins of the microcontroller, in particular, we can just get the Jtag device to send the right signals to the flash memory to program the data we want into it. So these days, Jtag, especially for hobbyists, is mainly used for programming and configuring boards. As already mentioned, when we develop our Verilog code in Quartus and we've compiled it and generated the configuration file, when we go to load it onto the DE1 SoC board, then we're actually going via the Jtag interface.